Well, thank you to the organisers for having us here today as well. We're excited to be here to talk about UAV awareness, and particularly for our application in landfills. When we talk about awareness, I think we're really talking about being limited by what we can see. And so as we enter into a new technological revolution, as many are calling it, with the use of UAVs or drones, really it's giving us an in-sky perspective of being above the earth at much more reasonable cost compared to conventional aircraft. So that's opened up a whole new field of research, technology, and also application. So I'd like to talk to you a little bit about that today. And we use a octocopter drone you can see here. It's a V-rotor design. And we use that for different reasons on landfill sites. Because there's a lot of bird life as well, so having a lot of rotors is a little bit of a deterrent, and they stay away, so we don't have to harm any of the nature whilst going about our job. And also it enables us to operate in smaller areas without takeoff and landing limitations. So we find that this type of UAV is very useful on a landfill site. Now, I think for us with UAV technology, we can look at it as just a camera or providing addition to help with surveying. But I think the surveying is always going to be around. Conventional surveying, you can never replace the role of surveyor. What we see a UAV as is really creating awareness. So we see it as like a diagnostic system, kind of like you go to your GP regularly, and by having regular checkups, you can tell if you're healthy or unhealthy, make changes if you need to. At Reverse Mining, we believe the same thing. By utilising UAV technology, we're actually able to have a look at a landfill site, work with operators, see how healthy or unhealthy it is, and then make the changes required before they get out of hand, or like Gavin's talked about, different legal ramifications for that. So we're about managing the full anatomy of a landfill. So we bring 8 parts of technology together into an IT package that can be basically finger point operated by operators, surveyors, and also key landfill staff to ensure that they can meet their tasks or goals. And so we bring 25 years of landfill experience and use 3D parallelopiped mathematics to basically try and maximise the cell life and minimise the amount of stormwater you've got running into leachate. And we've achieved up to 70%. And also by increasing the life of the cell, so minimising the amount of cover, we're able to save millions really annually across different landfill sites. So I've made a short video to show with you today about basically a landfill site that we've been at down in Victoria, and we're going to have a look at a few of the different ways we can actually use this technology to help landfill sites. So I'll start that now. You'll have to put up with my commentary. If I could do a David Attenborough voice, I would, to keep it a bit more interesting. But we've got some great things happening with UAV technology. So here you can see a few of the panoramic shots we've taken of this particular site from the air. And by flying over the top of it with the UAV, we can actually stitch all those images together into a 3D model, which is what you're seeing here right now. So the way that actually happens is the UAV basically flies a pre-established pattern. So we set up a GPS grid according to where the site is. We check in with the local regulations with the government. There's a few hoops to jump through there to make sure that it's all legal. Once we get the UAV started and flying along its pattern, it basically will take a series of images, and then we run it through a very powerful computer to stitch everything together and produce the whole model, which you can see there with contours as well. And by creating that, basically it allows us to make a quick data analysis of different parts of the landfill site. So we can plan batters, roads, stockpiles, drainage, all in this 3D interactive environment, which definitely helps with awareness and also makes it easier for operators to plan. So first thing we've got here is a stockpile measurement, as you can see. So we can actually measure the volume accurately to conventional surveying standards. And then we can calculate the cover being used on the active tip face. You can see we've simulated part of that cover being removed, and then we can basically apply a volume calculation and compare the difference between the two. As we move around the site, you can see being interactive and being able to drag around, it actually makes this technology very useful for training, for staff training, so we can provide that and also enable operators to teach staff for look at problem areas, and also as they move through the landfill site itself to diagnose any ramifications or things that need to be changed. And like we said, preempting any problems before they become more serious. Here at the active tip face, we can measure the area and also volume. And so what we've done there is basically produce a very accurate point grid that allows for all the undulations in the rubbish and so we can then export that and use conventional surveying as well. And here we've got some measurements, so we're measuring the height, length, breadth, and we can also measure angles and slope degrees, so we can adjust basically where we're putting the rubbish and then where we're putting the cover. And these adjustments can be made much more regularly through the use of this technology on a much more regular basis. And so we're calculating the area of the face there. So we go fly down now to the leachate ponds on this particular site. And using this technology, we can also calculate sinkage across already completed cells. So with the leachate planning, if we fly over prior to the leachate being used, or when we're actually doing the design, we can actually work out the volume as the leachate fills up, which helps when you're looking at processing costs. And we can also look at, okay, how far have we got to go here before we need to consider either building a new pond in advance or some other options. And here you can see on the 3D model, we're just having a look at exactly where the land around that leachate is running. And that gives us a good idea about when we're running pipes and whatnot to make sure that we're using everything as efficiently as possible. As we move over the leachate pond, this is actually a secondary pond or collection that's being constructed. So it's a new section. And by regularly overflying this with a UAV, we can actually perform calculations on progress. So we can have a look, here's a actual 3D model of progress on that construction. We can look at the volume that's there, what we're looking at with regards to material being removed, so how far along we are, and you can compare that then as well to contractors' estimations. This particular site had a bit of a batter collapse over here, which you'll see shortly. And so very important, obviously, to achieve those final contours as accurately as possible. And so through utilising a UAV technology and also our calculations, we can actually provide GPS waypoints across the entire site to help manage those final contours for your operators, and also to keep things as accurate as possible to prevent something like this, which obviously can become very expensive when you're looking at carting that across to another active cell and also fixing that batter. And what we're calculating here is basically the exact slope of the batter as it goes down. So you've got degrees, you've got your RLs, you've got your heights, and from that gives us a much more accurate way of measuring it. Here we've just got a simple simulation. That stormwater looks awfully clean, but that's basically having a look at, okay, if we simulate a peak rain event, where's the water going to run and what's it going to look like? As we come across now to the side of the site, we can also measure volumes of basically anything on site. So here we've got some vegetation, and we're also measuring the area here because that's a very important consideration with water runoff. So we're able to have a look at that, see where the land is actually lying and where it's running, and again, that aids with planning how you want to plan your landfill site, where you've got your stormwater running, minimising again your leachate and minimising your costs. These guys were actually partway through constructing their new cell, which you can see here on the left. And again, through utilising this 3D model technology, we're actually able to fully plan a cell in advance and then to regularly check up how we're actually going with that plan. So we can fly overhead the cell using the parallelopipe mathematics and work our way through the cell and maximise the life that we can achieve in that cell, and therefore the longevity of the site. So I've got to keep it very brief. I've only got 7 or 8 minutes, but that's just a couple of things that we can do as reverse mining, utilising the UAV technology and creating awareness on site. So if you'd have any further questions or about your site, please come and have a chat to us, get a business card. Now, obviously, this technology is great, but we needed to prove it to tolerances to make sure that we can use it. And we have done that successfully, and we work with private surveying firms as well, but we really wanted to prove it in a council setting. With an authorised, well-known council up in Queensland at Logan. And so we've been working with Scott Grattan, who actually created a test for us to prove this technology and prove the accuracy, which is great. So Scott's from Logan, and he's been an integral member of the survey section at Logan City Council for almost a decade, and he embraces new technology across the board to help create survey information and benefit his community. So please welcome Scott.
Thanks, Ryan. Good afternoon, everyone. Thanks for coming to listen to us today. As Ryan said, my name is Scott Grattan. I've always loved looking into new technology, and I'm lucky that I get the chance at Logan to actually look into ways to build on and improve the existing practices we use for surveying. So that's why I'm happy to come here today to talk to you about the case study that we did, which was the UAV, or unmanned aerial vehicle, and show you a bit of what data it can produce, including 3D surface models. Just a few quick facts about Logan. We're nestled in between Brisbane and the Gold Coast in southeast Queensland. With 300,000 people, we're actually the 5th largest local government council, and we're about the 6th largest by size, I think. As a result, we end up producing quite a bit of waste, but not quite as much as San Francisco was producing this morning. Our Browns Plains waste and recycling facility covers over 100 hectares of land and handles over 200,000 tonnes of refuse each year. Over a quarter of that is recycled, and our gas cogeneration plant provides enough power for approximately 2,000 homes. Today, I'm going to talk to you about a recent case study we conducted where we trialled using the UAV, like the one behind me or the one sitting on the chair here, to collect spatial information at Browns Plains. Some of you might already know Grant Lacey from Reverse Mining, whose assistant made this possible for us. My talk will be particularly relevant to anyone that creates or consumes spatial data during the management or planning of landfill areas, but today I'll mainly be focusing on the surveying accuracy aspect of that information. Hopefully by the end of my talk you'll have seen a different approach to collecting spatial data and potential uses in your own areas. Feel free to raise any questions as we go along, and I'll try to answer them. In order to test the data properly, we wanted to do a real-world live project. We didn't want test simulations or demo flights or anything. We actually wanted to get our hands on a real project. So we set out for the quarterly volumetric report at the dump, which we do every 3 months, just to give the guys an idea of how their weigh bridges are measuring up to what's actually going in the ground. And if we're going to use this information in the future, we really needed to test the consistency and accuracy of the flights as well, compared to our current standards. This included working out what some of the limitations might be, such as how many ground points were required, how the weather affects it, or how vegetation and other non-ground points may affect the 3D surface model. And it turns out that high winds tend to blow away the accuracy. It was a good opportunity for some other departments within council to also see the data we could create and explore uses in their own branches. Our environmental management group and compliance sections have already started looking at the use of drones for where we've had illegal tree clearing or introduced soil into waterways or flood zone areas to calculate those volumes and issue infringement notices. On the morning of the flights, I went out and put a couple of ground control points down. And we put 6 ground control points using existing site control we already had at the tip. These ground control points were just paint marks. They're about 300 mil square, which that's actually a direct screen capture from the imagery we got, so very clear and easy to see. And for the actual flights, Reverse Mining has a CASA commercial pilot to do to all the flights for us, and that makes sure that all the aviation regulations are met. We were then able to stand back, let the UAV do its work. Rather than walking about the site amongst the machinery, we just stood back and it hovered above without interruption. In order to have enough data to test the suitability and repeatability, we decided that we wanted 2 completely separate flights, a morning and an afternoon flight, and this allowed us to compare not only against our data, but one directly against the other. After the flights, we were able to produce a 3D surface model and have the imagery, brand new imagery, draped right over the top. When I brought the data in to produce that image, it took about 10 minutes. To create a base model for comparison, we completed a field survey using the current Logan City Council standards with conventional survey methods. This includes the location of physical features, such as the top and bottom of banks, change grades, and all the little blue points there are just surface points that we picked up in the field. And then we used 12D as our surveying package to work out all the volumes. Here I've overlaid the data that we've been given from the UAV flights. As you can see, the purple crosses there. The intensity from the UAV is far greater than what we would pick up in the field. I'll move on. And there's the triangulation. That's the green triangulation is the triangulation from the field pickup, and the blue is from the drones. We used the 2 metre grid because we felt that anything larger than that you started to lose a lot of surface detail, but anything smaller than that made the data a little bit too large and unmanageable on our PCs. One of the problems we ran into with the flight data, there was vegetation around the site and also stockpiles and machinery on site that we obviously didn't want to include in the volume calculations. So we had to go along and remove stuff like vegetation, stockpiles, and even the top of machinery. If there was any machinery working when it was flown, we had to remove those points. They're not included in the fill volume. Nobody really wants to get stuck into numbers, but they're all the checkpoints. We did various checkpoints. The top one up the top is the field survey, and as you can see, even with the field survey, if we didn't have a field pickup point near where the checkpoint was, then you can, because there's bumps, and it's not a perfectly flat world, unfortunately. It'd make my job a lot easier if it was. The middle one here is when we only use the 4 external control points, which you'll see on the next screen. It introduced a lot of area, and then the bottom one is the final flight using all 6 control points, and nothing actually came outside of tolerance, which was good. Here's the 6 control points, so you got the 4 around the outside and the 2 in the middle. So this was a comparison from the field survey to the UAV flight data using only the 4 external points, and as you can see, it left a significant error in the middle. The blue ring around the outside is within tolerance. We decided a 0.1 tolerance plus or minus was good, and then anything kind of outside that tended to lose accuracy. This is a comparison of the 2 flights, the morning flight to the afternoon flight, using the 6 control points. The bright green area here you can see, that's actually the active tip face on the day. So that's to be expected because that's where all the fill was coming in. And this little red dot you might see there, that was a dozer that was parked there in the morning flight. It wasn't parked there in the afternoon, so the afternoon flight was able to pick up the fact that a machine had moved. And this is the final comparison between the field survey and the corrected flight information. Unfortunately, because of winds, we had to do the flight a full week after the ground survey. So you can see that big green patch there, which was the active site. That's where all the fill was coming in over the week, and that volume was actually to be expected. It was about 3,300 metres cubed, which is about what we get in a week. And then the area around the outside, not only is it outside the control points, but it's actually down a batter as well, which helps explain the accuracy. So we showed that within the confines of the ground control points, we were having an expected error of less than 50 millimetres, and the ground control points, if you're using 6 ground control points, the difference between the field survey and the UAV flights was less than 1% difference for the quarterly volume reports. And I think I'm being moved on, so I'll probably end it there if anyone's got any questions.